Álvaro is an expert in protoplanetary disks, particularly observation analysis of these. He did his PhD in Madrid, followed by postdoctoral work at Boston. He was an ALMA fellow as well for some time, and now he is at Cambridge as a research associate. And today, Álvaro will be talking to us about unsolving planet formation.
Thanks, Rob. Well, sorry everyone about the technical issues. It's a bit ironic that there are some parts of the talk that have to do with neural networks and these high-level IT things, and then we couldn't even connect. So yeah, like Rob said, my name is Álvaro. I'm currently a postdoc at the Institute of Astronomy, and I work mostly on protoplanetary disks, mostly on observations also, and in particular ALMA observations. I took a look at the department's website, and I think there's not many people working on disks. So a lot of the talk is just going to be an introduction to protoplanetary disks, what we know, what we knew before ALMA came around. And then I titled the presentation like this because by trying to solve a few things, we ended up with more questions than answers. So I will also tell you about a couple of examples in which that happened. And I'm going to start with the mandatory figure for every exoplanet-related talk. As the exoplanets that we know of, the orbital separation in the x-axis and the masses in the y-axis. And the reason why I have this here, and I also have the solar system, is because this plot clearly shows that most of the exoplanets that we know of have nothing to do with what we have in the solar system. If we want to understand really the population of exoplanets out there, we need to understand how planets form. So planet formation and protoplanetary disks is crucial to understand this plot. And so that brings me to the outline of this talk. Like I said, the first two parts are going to be general knowledge about protoplanetary disks. The second part is updated knowledge about protoplanetary disks, and then these two particular studies that we did. And I'm going to start with what has been known for quite some years. Maybe you already have this picture in mind. So the way planet formation happens and protoplanetary disks form is you have your molecular cloud, gas and dust that's sitting somewhere in space. And for different reasons, part of the molecular cloud begin contracting under its own gravity. You form a protostar in the center, and then the surrounding material cannot fall directly onto the protostar. So it starts spinning, it forms a disk, and you have what's called a class 0, class 1 disk or object. It's a very embedded source. You have a protostar in the center with a disk that's still forming, but you also have dust, an envelope around it. Sometimes you see outflows. Typically, you don't see these objects in the optical. You have to go to long wavelengths to see them. And that phase lasts for about 1 million years. After that, we come to protoplanetary disks, which is the objects that I study. And this is just what happens when you remove the envelope. You just have all the material orbiting the star. You have gas and dust in there. And this phase lasts for 10 million years, more or less. And after that, you're just left with a planetary system, hopefully, because we see planets everywhere and we have to explain them somehow. And a debris disk, which is just similar to our Kuiper belt and asteroid belt, so mostly dust. I'm going to focus on the protoplanetary disk phase, like I said. And so in general, what we know about these disks is, well, they form from this molecular cloud. So the initial composition is similar to that of molecular clouds. So you have a gas to dust ratio of around 100. And the dust that initially joins or forms the disks is quite small, submicrons in size, which if you think about it, it's spectacular that you go from that to gas giants. That's over 12 orders of magnitude in growth to form gas giants. And that happens during the disk lifetime. The total mass is about a few percent of that of a central star. Typically 1-3% is what we find. Dust radius is, again, typically less than 100 AU. Some objects are bigger, and of course there's a bias. We like to observe bigger disks because we see more things. But typically what we find is most disks are less than 100 AU in dust, and in gas they're more extended because there is this radial drift. Large grains, so dust grains in the disk interact with the gas, and they experience some radial drift. They settle towards the midplane and move closer to the star. We'll talk about that a bit later. And they also flare. So as you move away from the star, they become vertically thicker. You can see you have temperature gradients, density gradients. The things that you have to take into account, they're not very simple objects to model. And if you want to understand how planet formation happens, you need to take into account all these different things. But we have our disk, and the disk disperses at some point. And there are two main theories. Well, there are many processes that could lead to the evolution of disks. There are two main competing theories. One is through winds, and those winds can be thermally driven or due to magnetohydrodynamic effects. So in one case, you have the radiation from the star or external radiation that's heating the material in the disk. If it gets hot enough, it can leave the system, and you have a wind, and you're losing material. And in the magnetohydrodynamic case, you have some strong magnetic fields that are just removing material from the system. That can also drive accretion onto the star, which is also observed. For quite some time, we didn't think, for whatever reason, we didn't think that was a very compelling explanation. We're not sure what the ionization fraction is in disks, but we think it's not high. So most of the time, we went with the second explanation, which is viscous evolution. So for those of you that work on any type of accretion disk, so around black holes, for example, you may be familiar with this concept of the alpha disk prescription. So you have a disk that has some sort of turbulence. The origin, at least in disks, is still debated. It's not clear where the turbulence comes from. But what does that turbulence does is the disk will try to spread out. So it will try to spread closer to the star, and then material is accreted. It will also try to spread away from the star. And through this process, you can also end up dispersing the disk. And the reason why I mentioned the alpha disk prescription in particular is it gives you a prescription for the type of structure that you expect in a disk. So you can use that to model the observations and see if it matches or not. And alpha is this parameter that parameterizes turbulence in the alpha disk prescription. And that will be important in the future. Regardless of what is the dominant evolutionary mechanism, we know disks disperse. And you can trace that by looking at different star forming regions. Each of them, you get an approximate age for them. And you can see what happens with the fraction of objects that are accreting at different ages. So that's what you see here on the left plot. On the x-axis, you have age. And on the y-axis, that's how many objects in different star forming regions are accreting. And you can see how the fraction goes to zero close to 10 million years. And the same happens if you do the same exercise with infrared X, which is a proxy for the presence of dust around the stars. So if you don't have objects with infrared X, you can infer that the disks are no longer there. We get more or less the same result. By 10 million years, most of your disks are gone. And that's especially relevant if you're trying to form gas giants, because once the disk is gone, there's no gas to continue accreting. So if you want to form a gas giant, you have to do it while the disk is still there. Terrestrial planet formation can still happen because you may have some planetesimals, but gas giants need to form while the disk is there. And that, all this story, it makes for a very good story. It makes sense, right? But of course, there are things that still didn't use too much. And one of that was the radial drift barrier. This is such an important problem that has its own problem. And the idea is gas and dust will interact, like I said before. So if you have a dust particle or a planet orbiting a star, it wants to do that at Keplerian velocity. But if you have gas in the disk, the gas will feel extra support from the gas that's closer to the star because it's hotter and denser. So the gas is orbiting at sub-Keplerian velocities. So you have dust particles that are trying to move through the disk, and they're going through this gas. They basically feel a headwind. So if you're a very, very small dust particle, you're just completely coupled to the gas. You will orbit at sub-Keplerian velocities. If you're a very large dust particle, and kilometer in size, I don't know if you would call that a dust particle, but you just don't care about the gas. You just go at Keplerian velocities. But for particles that have Stock number around 1, which happens in protoplanetary disks for particles that are millimeter, centimeter in size, they experience this drag and they start losing angular momentum and velocity, they spiral inward and get engulfed by the star. And this process is very, very fast. So what you see here is how long it takes for different particles to be engulfed by the star when you place them at different distances from the star. So if you focus here on this line, for example, on the light green curve, that's for a 1 centimeter particle. Planet formation models and dust growth models will tell you that you can get to maybe 100 meters in size in about 1 million years, depending on which mechanism you use, maybe a bit faster, but it doesn't matter because in 10,000 years, that particle is already gone. And this is a problem. We see exoplanets everywhere, but once you get to millimeter, centimeter sized particles, they just disappear. You can't make it past that. So this is where I'm gonna start talking about what we've learned in the last 10 years. And when I was preparing this talk, I realized that this makes me feel old, but I think I'm part of the generation that learned something during their PhD, and then 3-4 years after that, we really had a huge change in how we study and what we think about protoplanetary disks. So here are 2 observations of protoplanetary disks by the submillimeter array. This is an interferometer in Hawaii. And so these ellipses here you see in the bottom left corner, that's the beam size. So that's the resolution element. If you're coming from the optical, that would be your PSF. You cannot see details smaller than this. And for quite some time, for a few decades, this is what we thought protoplanetary disks look like. We can resolve them. They're more or less smooth. Some of them had a huge cavity in the center, which it was argued that that's because you have planets in there that are carving gaps. So, and everything made sense. And then ALMA came around, and it showed us that these objects actually look like this. They're full of gaps and rings. And I'm sure it's the case for many fields. I've worked at ALMA for 4 years, and I know it's, for people working on all the topics, it's also been a huge change. But in planet formation, it's really revolutionized the whole thing. And you may be thinking there was 2 examples, but no. What ALMA showed us is that basically every disk that you observe with sufficient resolution would show some gaps and rings, spirals, asymmetries. So what you're seeing here on the left, those are 25 disks. This is a continuum survey. So just tracing emission from millimeter-sized particles in disks. And these 25 disks were selected specifically because they didn't have any signatures of gaps or structure in them. They were thought to be smooth, boring, if you want, disks. To the left, what you see there, it's just a lot of gas observations for one single disk. It's not 25 or how many disks you have there. It's one single disk, only different gas lines. And you can see how the morphology of the line really changes depending on the local conditions in the disk. And of course, ALMA is not just ALMA. We also have instruments like GPI or SPHERE, which are coronagraphic observations, which you just block the emission from the star and you can see what's around it. So these are few disks observed by SPHERE. Within the Destiny's Large program, they're observing a huge amount of disks in scatter light. And scatter light is tracing small grains on they're basically floating on the upper layers of disks, and they scatter light from the star. But you see how it's full of structure. It's not just boring disks. And this has changed a lot of planet formation, starting with the radial drift problem. Because before, we didn't know how to make it past the radial drift barrier. Now, it solved itself. Because what's happening is not that the grains want to go to the center of the disk. They move towards pressure maxima. So if you have local pressure maxima in your disk, like some rings, that could act as dust traps. You can have your dust particles live there happily for much longer, grow to sufficiently large sizes that they don't care about gas anymore, and that's it. And we now see, remember, every single disk looks like this. This is actually a simulation done in 2012, before the beautiful ALMA images came. This is what happens if you have small perturbations in the pressure of the gas in the disk. You can form all these rings just by having this pressure maxima. So that solved perfect. Other thing we got is, or a huge census of disks. ALMA is very sensitive, so we've been surveying different star forming regions, and now we get fluxes, millimeter fluxes, which under reasonable assumptions you can turn into masses. You assume that emission is optically thin, so the millimeter flux is linearly related to the mass in the disk. And we've also been measuring radii. So something interesting that came out of this is we see how the masses of disks decreases with time. So here the curve to the right is a cumulative distribution of masses in different regions. And this line here, this is Perseus. This is the youngest star forming region of all this. And you can see that all disks are more massive than 10 Earth masses. And the green line here, this is superscope. This is the oldest of the regions in here. And these disks are less massive than in Perseus. You can really see the effect of time evolution in the mass of disks. And also, I won't go into a lot of details, but ALMA has also produced a lot of evidence, indirect evidence for the presence of planets. So by looking at the Keplerian rotation of disks, we can look for deviations of that, which is what this break, this kink here, show us. And the idea is that you should have something more or less continuous, like this arc. In this case, it's broken. And the reason why we think it's broken is if you put a 2 Jupiter mass planet there in the disk, it will create this perturbation. The models actually match this fairly well. And this is fantastic because we have access to a population of exoplanets that we can't detect directly. This is embedded in the disk. But we can see that they're there. And over there, to me, that's the most beautiful image ALMA has ever produced. Many of you have already probably seen this. This is a protoplanetary disk. You have a star in the center. But what matters is this little point here. This is PDS 70. It's the only system in which we know there are 2 planets in the cavity. And this little blob, that's centered around one planet. That's dust surrounding the planet. That's a circumplanetary disk. So it's something like the rings around Saturn, but way more massive. And probably that will lead to the formation of exomoons in the future. So I hope that has convinced you that in the last 10 years, we've really been changing the way we treated planet formation. But of course, when you have better data, you also have new questions. So one of them, and this is far from understood, is we are finding rings and gaps everywhere. And I told you this is great because it solves the radial drift problem. But now the problem is, what is causing these rings in the first place? Because this is a chicken and egg problem. We are saying, well, you have rings, they can trap the dust, and then you can form planets. But most people think that those gaps are formed by planets. So how did those planets form in the first place? And the second thing is we are seeing structures like this in very, very young disks, even in class 1 disks where they're still embedded. We thought planet formation took a couple million years, something like that. And now we see this in objects that are less than 1 million years. So we really don't understand the interplay between structures in disks and planets. And the other surprise is that when you take the millimeter fluxes and turn them into masses, and you compare those with the masses of exoplanetary systems, it looks like protoplanetary disks are not massive enough to form the planets that we observe. So this red area here, that's the masses that you get from disks, and in blue, those are the masses of exosolar systems. And there is, there's some tension in there. Maybe part of the solution is the third thing that we've learned is that protoplanetary disks interact with their environment a lot. We typically think of protoplanetary disks as isolated systems, but as you can see there in this scatter light image, you have this disk in here, but you also have this beautiful structure around it. That's material from the cloud that's still falling onto the disk. This is a more or less mature system. So what this tells us is you cannot think about disk evolution individually. You may also have late infall of material through the lifetime of disks. So this is where we are now. And now I want to tell you about a couple of cases in which by trying to help, we made things a bit more complicated. So for any of you that have been trying to ever fit models to data, you may have found yourself in this situation. The idea is if you have a large sample and you're trying to model complicated or complex systems, typically you have to make a decision. Do you go for a simplified version of your models and then maybe do some statistical analysis, or do you focus on just a few objects and really try to fit them properly? So this study, the one I'm going to be talking about, is dealing with SEDs, spectral energy distributions. Nothing fancy like the ALMA images I showed you before. It's just fluxes at different wavelengths. And this is the way an SED of a protoplanetary disk looks like. You have here that this is the photosphere, so the star. Everything else, this is excess coming from the disk, in particular the dust. So that tells us something about the disk. And I have these two plots here because those are two examples. Here in this study, they had a very large sample of objects. They were trying to model that and learn something about their statistical properties. They were trying to use Bayesian analysis, an MCMC process. But because of that, they had to, fix some free parameters, make some assumptions, and you end up with a simplified version of what you think is really happening. And in the other case, that's a type of study in which they had very detailed analysis with very complicated models, but they couldn't do any statistics. And actually, they have this sentence in the paper which says, even with 100 processors, it will take us half a year to model just one object. So we're not going to do the statistics. And so we read that and still thought, let's try. And so that was the point of this paper. We were going to try to model SEDs of protoplanetary disks, a decent sample of protoplanetary disks, without losing detailed models. So our sample was 30 protoplanetary disks in the region of Taurus, Eureka, which is 1 to 2 million years old. That's the type of data we had. So all those red points are photometric measurements for this disk. In blue, you have the spectrum from Spitzer. We also had some spectra in there. And the original sample was much larger, but we tried to go for the most simple type of disk. So single objects, no binaries, no edge-on disks, which are very hard to model. And we discarded everything that was known to have large cavities or substructures because that adds complexity to the model. So we were just trying to go with the most simple case. And for the models, we were using the models by Paola D'Alessio, the D'Alessio irradiated accretion disk models, which I will call DIAD. And the reason for that is these are very physically motivated models. They use an alpha disk prescription. Remember that I mentioned that if you have a viscous disk, that will tell you what sort of structure you can expect for the disk. It takes into account vertical hydrostatic equilibrium, viscous heating. It incorporates the settling. So these are decently complicated models of protoplanetary disks. The only problem is that each of these models takes about 1 to 2 hours to run. So I made the numbers. We had 13 free parameters in our study. If you want to explore a large parameter space, let's say just 10 values per free parameter, that means 10 to the 13 models that you have to calculate in a grid-based approach. Good luck with that. It's 10 to the 1 hour, it's impossible, right? Also, at least SEDs, but it's the case for many of objects, SEDs are extremely degenerate. They're the parameters that are important. Some of them, you really don't know what the value of the parameter should be, but whatever you choose is going to affect other parameters. So you want to do some Bayesian analysis, something that's statistically sound. You get the probability distribution for the parameters that you're fitting. The way to do that is with the Markov chain Monte Carlo method. If you're not familiar with that, don't worry. The only thing you need to know is that these chains depend on where you are in the parameter space. You evaluate the model, and then you decide where you move forward. So it's something that cannot be parallelized. You can run many chains at the same time and then put everything together. But even if you have infinite computing power, you still have to wait 2 hours every time you want to move forward in the chain. So I did the numbers, and they were not good. To me, it was 10 years per object. And my postdoc at the time was shorter than that. So that was not going to work. And the way to think about we try to think about it in a different way. And the idea is models are just functions. You have a set of input parameters, you give them to your computer code, you wait 2 hours in this case, and you get an SED, so a collection of fluxes at different wavelengths. That's just a function. It's a very complicated function. It takes the computer 2 hours to solve, but it's a function. And artificial neural networks are very, very good at learning functions. They're universal function approximators, which means that if you make your network complex enough, you can approximate any function. So that was the idea we had. We're gonna try to teach a neural network that very complicated function so that we will give it the same input parameters and we will get the same SED. And for that, the neural network that we created looked something like this. So you have the same input parameters that you give to diet, stellar parameters, disk parameters, gas parameters. Then you have machine learning jargons, a couple of hidden layers. You just have an output layer. Basically, you input this and you get 100 values, which is the flux at 100 wavelengths. You need to teach the neural network or to train the neural network. And for that, you need to know in places in the parameter space what the input parameters were and what the output parameters were. So there's no escaping to running models. And we run 50,000 models everywhere in the parameter space. But this could be parallelized. You just run in models covering the parameter space, and then you just give that to the neural network, and the neural network learns that function. And it works. I cannot tell you how happy I was when I saw it first, because I had been fighting with this for several months, and it didn't seem like it was going to work. But in this plot, you may be able to see there's a blue line behind all those yellow dots. That is an actual model from DIA. That is, we ask the models, can you give us the SED for this combination of three parameters? And those yellow dots are the prediction from the neural network. We are off by less than 5%. And that's typically the uncertainty you have in photometric measurements anyway. The only difference is that this calculation, those yellow dots, you can get in 10 milliseconds instead of 2 hours. So now you can play whatever game you want of statistics, you run your MCMC, and these are the fits, some of the fits we got. And I have to say, these fits are better than some of the fits I've seen for people working on maybe one or two objects and spending a lot of time trying to fit just one single object. So it worked very well. I won't go into the details about everything we learned, but I want to focus on a couple of things that were interesting and a bit puzzling. So the first one is one of the parameters we get of the modeling is the masses of the disks. And the masses we get are systematically higher than the masses that the millimeter surveys gave us by about a factor of 3. I think what this is telling us is we've been operating under this assumption that the millimeter emission from protoplanetary disk is optically thin, and that may not be the case. You're not sensitive to all the material in the disk. But this is great, because this solves this tension between the masses of exoplanetary systems and protoplanetary disks. And the other interesting thing is alpha was also one of the parameters in our model. Remember the turbulence of viscosity in our disks? And we were getting values between 10 to the minus 3 to 10 to the minus 1, which may not tell you much, but this is about 1 or 2 orders of magnitude higher than what actual or more direct measurements. Every measurement of alpha is indirect. But observational evidence for alpha in disks is closer to 10 to the minus 4, 10 to the minus 5. So what this tells me is probably just an alpha disk prescription is not enough. If you want to fit your observations with an alpha disk prescription, you need to change alpha in a way that doesn't match the observation. There's something we're missing. And I think the solution to this is these quids, which from other studies are also getting more attention recently. So probably you cannot understand disk evolution only with an alpha disk prescription. And then with this neural network, other collaborators have applied it to other star forming regions. Now we've modeled hundreds of protoplanetary disks, and the results are very similar. So I think this is a very interesting approach. And what I want you all to take home, if you don't care about protoplanetary disks at all, this type of approach can be used. There's nothing in here that means you have to be working on protoplanetary disks. You can apply this to whenever you have complicated models and you can calculate a lot of models, you can think about surrogate modeling. So if this is something you're interested in, come talk to me later. And I'm going to finish with a completely opposite approach. Just instead of trying to learn something about statistics, I was focusing on one particular object that was originally very interesting. So this is MP-MUSE. This is the second closest protoplanetary disk to Earth. The closest protoplanetary disk to Earth is called TW Hydra. It's probably the most studied disk in all planet formation studies. And it's beautiful. I'll show you an image later. But when I came across this, these two images are scatter light images of MP-MUSE. So the central emission from the star is blocked. And in both cases, you can see it has this outer ring. So we thought, well, this is a fantastic target to study radial drift, because maybe we can see differences in dust properties in the outer ring and in the central region. If radial drift has really happened and large grains are concentrated in the inner regions, we don't expect the same dust properties in the outer ring and in the inner regions. This is also a solar analog, so it's 1.3 solar masses. So you can make connections with the sun. So it turned out that this object had never been observed by ALMA before. And we were hoping for a spectacular image. And this kind of spoils what we found. If you don't want to read the whole title, an alternative is the disk is so boring that it makes it interesting. Because we did not find any structure at all. These are 3 continuum images at different wavelengths from ALMA. The ones to the right don't have as good as angular resolution as this one. This image has a resolution of, I think it's around 4 AU, so it's really high angular resolution. And yeah, you can see that you have the central emission, then and it looks like there's a break in the emission here and then a halo, but there are no gaps, no rings, nothing. This was really surprising. We also observe a lot of gas lines. In the gas, typically you don't see as much structure as in the dust, but we do find that the disk is more extended radially than the dust. So this contour here marks the continuum emission. So this, and you can see in gas the disk is about twice as big, which is in line with expectations of the radial drift. So that's total intensity emission for different lines, and there to the right you have the Keplerian rotation that we can measure with ALMA. And if you fit a Keplerian disk, you get a mass of 1.3 solar masses, which is independent of isochrones. So it's interesting that you kind of escape all these degeneracies with evolutionary models of stars. But if you put them in evolutionary tracks, that gives you an age between 7 and 10 million years. So it's a fairly old disk, but still is very gas rich. It has a lot of mass. We measure different quantities. We were able to tell that the gas to dust ratio in this case is closer to, it's between 1 and 10 instead of 100, which is what we originally assumed for disks. It's also very flat. So all of this is consistent with the disk that's quite evolved. But yet, when you compare the radial profiles, so this is gas and dust, like I said, there are no gaps. It's just smooth. And you see two lines here. The red one is just by calculating the radial profile from the image. So you take this and you just put some ellipses and that's it. But the orange one, that's using Frank, which is a software that uses the visibilities. Visibilities are the native measurements of interferometers. When you see an image from ALMA, that image has been synthesized or processed. If you work in visibility space, you get something back. You don't lose as much spatial information. So this profile probably has a resolution of about 2 AU, and still down to 2 AU, we don't see gaps and rings in a 7 to 10 million year old disk. So this is the only disk that has been observed with this resolution and shows no substructure, at least to my knowledge. And we don't understand why. So this is TW Hydra. Remember the closest protoplanetary is to Earth. You can see all these beautiful rings and gaps. If you put TW Hydra at the distance of MP-MUSE and observe it with the same resolution, you get this black profile. And you can definitely make out at least two gaps, probably the gap in the center, because the W has this one AU gap there. Still, it looks nothing like MPMUS. So does it mean that there are unresolved structures in MPMUS and they're just so small that even with 2 AU resolution, we don't see them? And there are some limits to how packed those structures can be. But if that's the case, then is this also happening in other disks? Are disks just full of substructures and we just don't have the resolution to see them? Are substructures just not visible because the disk is still optically thick? If the substructures of these gaps happen at the disk midplane, which is where planets are forming, but if the disk is optically thick and the line of sight basically stops before it reaches the midplane. So if substructures might be there, you just don't see them. But if the disk is still optically thick at 10 million years, which is when the mass is supposed to have, is getting close to, the disk should be disappearing, then all the masses we're measuring are just, we're hopeless. There's no way to calculate the dust mass, at least not this way. And the other option is, no, MPMUS really does not have substructures. But if it does not have substructures, then how did the disk survive for 10 million years without substructures retaining the large grains? And the other question is, what was that ring and gap that we saw in scatterlight? And we just have some hypotheses so that we don't really know if this is a gap. And there are different studies of the system that have been trying to find planets in it. We can place a limit of around 2-3 Jupiter mass planets. And this is a fairly large gap. This is 40 to 80 AU in radii. So you need a very massive planet to carve a gap or a multi-planet system. But it doesn't look like this is caused by a very massive planet in the disk. It could also be that there is some dust in here, just slightly smaller than what we can see with ALMA at this wavelength. So if we take additional observations at shorter wavelengths, we may begin to see some emission in the outer ring. And it could also be that it's just a shadow. So if you have a disk and the inner disk is puffed up for whatever reason, remember this is a scatter light. So that's light from the star bouncing off on the small grains in the disk atmosphere. So if you have a puffed up inner disk, that will cast a shadow. We don't know. And we have new ALMA observations that have been just taken at shorter and longer wavelengths with similar angular resolution. So maybe in about a year, I can tell you what was the solution to this. So I'm gonna leave you with this. I hope I have conveyed that we're really going through a revolution in the field of planet formation. There are still a lot of things we don't understand. We don't really know what the masses of disks are. Winds seem to be important for disk evolution. And we really don't understand these substructures. So we don't understand how substructures are present so early. And at least for MPMUS, in my case, I don't understand how MPMUS has no substructure for a disk of its age. So thank you very much. And if you have any questions, I'm happy to take them.
Thank you, Álvaro, for an excellent talk. Any questions from the room?
Yep.
Fascinating talk. Thanks for that. I enjoyed that. Can you quickly show us again this gap you were talking about? I think that went a bit fast.
You're talking about that one?
Yeah, exactly. Yeah, okay. So the gap is in there. So this is what you're saying is it's completely smooth and continuum in ALMA, but you see a kind of a ring and a gap in.
Yes.
For a scattered light. What about, you say it's not been observed by ALMA before, so you don't have any ALMA gas traces yet?
We do have this.
Oh, that one, okay.
So I don't have an image showing the scatter light image and the ALMA observations at the same time, but basically the gap that you see in the scatter light image is around here. So it's at the edge of the ALMA continuum, and we see this typically in disks. Small grains stand as far out as gas because they're coupled with the gas. So the ALMA continuum emission would go around here, and then you have this gap. We actually have an explanation for this that has to do with shadows. So what we think could be happening is in the radial profile, if you check the radial profile here, that's where the ALMA continuum emission ends. This is where we think large grains are. And then here in the disk, there's a change in opacity. You can have small grains here.
Right.
If the disk becomes suddenly a bit hotter here, you can have the disk flare or the scale height increase again. And then the disk is coming out of the shadow if you want a larger radii. So that's a possible explanation. We run some models. It seems like it could fit, but we don't see any evidence for a change in temperature, for example, in the gas lines that we have. So I'm hoping we can answer that with the new observations that we have coming.
The other comment I was going to make, which is something I've drone on about to my colleagues a lot, but we don't understand viscosity, right? Especially at these large radii. Hence, that could be part of the solution to all of these problems. But at the same time, if there's no viscosity to create a radial drift, that solves that problem. But then you kind of have this, you go back to your problems with your disks and your rings and your gaps anyway. So,
yeah,
how your accretion occurs and how these form. So, yeah.
Yeah, I don't think we have a good prescription for protoplanetary disks. I think now, for decades, people didn't pay much attention to winds, and in recent years, after seeing the ALMA images, basically you see all the structures that wouldn't be there if the viscosity was or turbulence was very high. They will disappear. So now we think viscosity is quite low in disks, at least in protoplanetary disks. So something else needs to be helping disks evolve, and that's why disk winds are making a comeback now.
Yeah, but those are normally relatively far in, aren't they? If we're getting out to this kind of 60, 80 AU radii, do people talk about disks as far out as that, or disk winds as far out as that?
No, that's a good point. No, I don't think that typically is for disks is probably something in between. Yeah.
Mike, I'm very intrigued by your disk SED models. So one question I have about that is about the viscosity alpha parameter. How does that affect, like, how well are you able to determine that from the models?
That's
I guess, like, that would, like, it's obviously very important in disk evolution, but I'm wondering, in the actual SED, what effect that has, and how can you distinguish that between reprocessed emission? Okay,
yeah, I'm sorry, I have some figures in the paper showing how each parameter changes the SED. I can show you later. But in terms of how well we can constrain them, I think in most cases it was within one order of magnitude. So the posterior distribution is fairly broad, but the idea is that then you put together all the 30 disks that we were able to model, you put them together and have the combined statistical distribution of alpha values. And it was quite skewed to very high values. So that's where we're thinking that's not matching what other observations are saying.
Do you have any sense of how, like, a higher alpha would change the shape of the SED?
And this was a few years ago, so I don't remember exactly, but I'll show you I have a figure to show you that shows exactly that, how alpha changes the SED. Yeah.
Are there any other sources you can use the shadowing explanation for?
Actually, TW Hydra has, it's hypothesized that it has a shadow. So in scattered light, the shadow didn't look like a ring. It looked more like just pizza slice. And there's some claims that they saw it move. And the idea is that there's something in the inner disk. If you have some puffed up structure that is rotating quickly, you can see the shadow move azimuthally in a span of a few years. I don't have any source in mind for which would say that maybe an azimuthally symmetric shadow. There are some models that produce this. People have looked at the effect of having a puffed up inner ring, but I don't know of a specific object that would look like that. Final question.
So about the SED again, I was wondering, is this available publicly?
The code, I'm afraid it's not, because the diet models are not. But now, if you're familiar with MC-FOST, which is a radiative transfer code for disks, they've done something similar. So really, if you have a model of whatever it is and you can run a lot of models, try this, because then you have a Python function that gives you instantly the whatever your model does. So they've done that for MC4s too, and that is publicly available. You can just get SEDs and very quickly. Yeah.
Based on that, how confident are you that the neural network setup you've used is the appropriate one?
Not at all. I didn't know when we started working on this, I didn't know much about machine learning. So one of the co-authors was an expert. The input I got was most people just try. So I don't think there's a specific prescription as to how many layers or how many nodes you have to have, but it worked very well. Maybe we could have optimized that and trained the neural network with half of the training sample. I don't know, but with what we had, it seemed to work.
Okay, then let's thank Álvaro.
No, thank you. And sorry about all the technical issues.